And now it's my pleasure to introduce today's presenter. Pam Harris is shifting the way we view and teach mathematics. She is a mom, former high school math teacher, university lecturer, and the founder of Math is Figureoutable. Math teachers around the world rave about her online Building Powerful Mathematics workshops. For over 20 years, Pam has been helping leaders and teachers reach more students in less time so that students math with confidence and success. She is also author of Developing Mathematical Reasoning, as I said, which will be hot off the press next week and the topic of today's webinar. And now I will turn it over to Pam Harris.
I was driving home and I was thinking really hard about a conversation that I had just had with my kids' teachers. They said to me, "Hey, Pam, we've been receiving the message that we don't want to give kids math anxiety, so we should stop giving kids timed fact math tests." Well, we don't want to give kids math anxiety, so we stopped giving kids timed fact math tests, but now we're noticing that kids don't know their facts anymore. Is that a problem? As a high school math teacher, I was like, that's a problem. Kids need to know their facts. But just like you, I also don't want to give kids math anxiety. So I was troubled with this and I was really thinking hard about it. I drove home, drove up in my driveway, walked in my house, and I smelled a double fudge chocolate Pop-Tart. That means my kid's home. And I was like, hey, you're in fourth, fifth grade. And I think to myself, do you know your multiplication facts? But in that moment, I just chose one at random. I said, hey, do you know your fives? I will never forget. He looked me straight in the eye and he said, no. Math teacher mom panic. Because if my kid doesn't know his multiplication facts, maybe none of the kids know their multiplication facts, and I'm ramping and he can tell. And he's like, Mom, you don't have to know your fives if you know your tens. I said, what? He said, you don't have to know your fives if you know your tens. I said, dude, I heard what you said. I don't know what you mean. What do you mean by that? Give me an example. He goes, okay, let's say you don't know 9 times 5. 9 times 10 is 90, and 5 is half of 10, so half of 90 is 45. And I was like, that is 9 times 5. Good heavens, does that work all the time? Give me another example. Okay. He says, how about 5 times 23? Y'all, not the example I'm thinking of. Like, I'm thinking, do you know your single digit facts? When he's playing around with a pattern to find 5 times 23. Y'all do it with me really quick. What is 10 times 23? Do you want to throw that in the chat? 10 times 23 is? Throw that in there. Yeah, a lot of people we got that zero thing. We could talk about the place value behind it, but for now, we're just going to use it. 10 times 23 is 230. If 5 is half of 10, what's half of 230? Throw that in the chat. Yeah, some of you beat me to the punch. Is that 115? Now, does anybody want to check to make sure? Does it make sense that if you have 10 groups of something and you cut it in half, you'd have 5? Like, my kid was playing around with a pattern that he could find 5 times anything. Y'all, in that moment, I was really clear that my kid was thinking and reasoning using relationships. He was confidently, logically reasoning through problems. And then I thought of my high school students who were not. I mean, for the most part, they would do what I asked them to do. I would give them the rule and the steps, and then they would mimic those steps. But they were doing different mental actions. They were rote memorizing and mimicking different mental actions than what my kid was doing. And in that moment, I thought to myself, I wonder if we could purposefully create what he was doing in my high school students. But let me be really clear. I actually, in that moment, wondered if I could create him in me, because I wasn't doing the kind of mental actions that he was doing. So I dove into the research. I read journal articles and I read research studies. And at the same time, I dove into my kids' classrooms. That's why I was on the campus that day, working with kids. Everything I read, I experimented and tried out. Because of my background in higher math, I was able to sift through a lot of less helpful research and find that there is a real mathing way to teach. I'm Pam Harris, and I believe that math is figure outable, and we can teach it that way. For the past 20 years, I've been helping teachers and leaders just like you get better results and have the confidence to reach more and more of your students. Thank you so much for joining me today. Today in this webinar, I'd like to accomplish three major things. May I teach you three things today about developing mathematical reasoning and avoiding the traps of algorithms. First thing I invite you to do today is, what do I mean by intentionally creating what my kid was doing? I'm going to call that mathing the way mathy people actually math. What is that like? Second thing I invite you to do today is to see the shark. I'll talk about that later. And then lastly, how do we avoid the traps of algorithms? So we're going to do those three things today. May I invite you right now, as you think about the story that I just told, true story, where the teachers say, just like you, we don't want to give kids math anxiety, but we are kind of worried that now kids aren't actually learning what they need to learn. In that story about 5 is half of 10, and you don't have to know your 5s if you know your 10s, what in that is either resonating for you, or what do you have a question about? What's either resonating for you, or what do you have a question about? Maybe put 1 or 2 words in the chat that's something that resonated for you, or you have a question about. Go. What's either resonating for you, or what do you have a question about? Connections. A lot of my students can't do halves. I wonder what they can do. And I wonder if we could then have with them, have is a funny word in the English language, we could find half until they can then actually find half. That could actually be a real thing that would be an important thing to help develop in students. Importance of fluency. We might talk about the definition of fluency later, because I think most of us have a different definition than each other. Might be talking past each other. Patterns, reasoning. Let me be really clear that my kid was not coming up with that pattern because of some new cool teaching he had. Nah, he had same old, same old. For some reason, he was kind of able to run into, oh, just so you know, I'm kind of starting number 1. What does it mean to math the way mathy people actually math? Now, careful. I'm not saying that not everyone's a mathy person. In fact, I think we all have the math gene. What we don't all have is the fake math gene. In other words, I was pretty good at fake math, what I now call fake math. I memorized a lot of stuff, and I mimicked the teacher when they gave me steps to do. I was pretty good at that. Imagine my dismay as a high school math teacher when I realized what I was actually good at was fake math. And I wasn't really mathing at all. I used to think that what people were doing in their heads was the algorithm, that they would just keep track of the little crossy outies and ones. No, that's not what they're doing in their head. They're doing much more like what my kid somehow naturally was doing. I think we all have some natural talents. Some of us are more artistic than others, and some of us are more musical, and some of us are more mathematically inclined. But that doesn't mean that we can't all do art, and we can't all learn to read, and we can't all do real math. So what does it mean to math the way mathy people actually math? What are the mental actions that mathematicians actually use when they're doing math? Because I'll tell you this right now. Ready? You know what they're not doing? They're not mimicking. They're not taking what someone else did and then just following those steps and circling their answer at the end. It's not what mathematicians do. You might be like, Pam, what do mathematicians do? Well, here's an interesting study by a researcher named Ann Dowker, who went to a bunch of professional mathematicians who do math and they get paid for it. And she said, hey, do you mind if I ask you just some math questions, and then I'll just kind of take note of how you solve it. I'll just kind of look over your shoulder, or I might ask you how you do it. She asked them a bunch of math questions. What percent of the time do you think those mathematicians used one of our traditional algorithms? They mimicked steps that someone else had come up with. I mean, they're mathematicians, so maybe 50% of the time, maybe 75% of the time, 4% of the time. Y'all, almost never. What in the world were those mathematicians doing the other 96% of the time? Well, let's do that. First thing we're going to do tonight, let's math the way mathy people actually math. So you might want to grab something to jot something down. If you're like me and you can keep track of your mental thinking by just like having like jotting something down, totally legal to keep track of your mental thinking. However, if when we do this problem, you find yourself kind of just going through some steps that your third grade teacher told you, maybe in that case, put your pencil down and say to yourself, I didn't have a pencil in my hand. What could I do to find an ish answer here? I'll quote Joe Bowler. What could I do to kind of get like, and then maybe pick your pencil back up and keep track of that thinking. All right, so here we go. I'm just going to change my input really quickly. You should just see a blank screen now. All right, super important question tonight. Ready? Anybody like gum? Yum, gum. All right, so many people chew gum. If you don't, it's okay. You don't have to. But check it out. If I had a pack of gum, and in that pack, there were a bunch of sticks of gum. And in this particular pack, there were 17 sticks. Can you picture that? It's not the little squatty, like fat ones. It's kind of the long, skinny sticks of gum. And in this particular pack, there were 17 sticks. Kind of random why anybody would put 17 anythings in. But anyway, they were selling these packs, 17 sticks. You can picture that pack of gum. So if we have one pack of gum has 17 sticks in it, how many packs of gum would 100 packs have? Everybody thinking, everybody thinking. Go ahead and throw that in the chat. How many packs would 100, excuse me, how many sticks would 100 packs have? People are throwing some numbers in there. By the way, it's not a race. You can take your time. If you don't want someone else's answer to interrupt your thinking, just don't look at the chat. Like, keep your eyes on me, think, and I'll try to give you enough time to think. So often we know that if I sort of scale that number times 100, scale the number of packs times 100, then I could scale the number of sticks times 100. And there's this kind of cool thing in our number system where if we multiply by 100, we could call that number 1700, have 1700 sticks. Now, again, we could talk about that place value pattern, but in the moment, we're just going to sort of use it. You guys are adults, you're using it. We're just going to kind of take advantage of it right now. So we've got 100 packs of gum, have 1700 sticks in that 100 packs of gum. What if we only wanted to have 50 packs of gum? Everybody thinking, everybody thinking. You can go ahead and solve that any way you want. How would you find the number of sticks in 50 packs of gum? So remember, don't look in the chat if you want to think about it a little bit. So everybody's thinking, everybody's thinking. I wonder how you're thinking about this. I wish this was more of an interactive webinar and I could actually call on you, but I'm super curious. Well, Heather, you put in the chat, she said divide by 2. Divide what by 2? I almost wonder if Heather's saying, well, Pam, if you've got half the number of packs, then you would need half the number of sticks. Oh, that seems kind of helpful. That you could actually use what you know, use that 100 packs to help you find 50 packs. Well, that seems kind of helpful. Uh-oh. Somebody said earlier, what if you don't know how to find a half? Well, let's go there for a second. If we had to find half of 1700, what do you know? I would ask a kid. Kid says, I don't know what half that is. I'd say, well, it's 1,700. What do you know? Most of the time, I find that students will say something like, well, I know what 17, sorry, I can think. I know what 1,000 divided by 2 is. And I'll say, well, what is 1,000 divided by 2? And they'll say 500. And then I'll say, what's left over? And they'll say 700. And then they'll say, but miss, I don't know what half of 700 is. And I'll say, okay, what do you know? And often at that point, kids will go, well, I know half of 600. And I'll say, well, sweet, what's half of 600? And they'll say 300. And I'll say, well, what's left over? You got 1,000, you got 600. You got 100 left over? Do you know half of 100? Kids will say, well, yeah, that's just 50. And then I'll say, okay, here's the hard part. What is 500 and 305? And bam, we're getting your 805 that a lot of you guys were writing over there. Is that right? Is it 805? Is that a way? 805. That's a 50. Just smile at me while I'm in front of a bunch of people. Is that 850? Yeah? See, when I wrote it down, that it wasn't reasonable all of a sudden. So if a kid doesn't know what half of 1700 is, I'm going to ask them, what do you know? And I'm going to represent what they know. Well, several of you are writing different things down. Now, you might have known that 1700, you might have said, well, I know what half of 1,000 is, and I know what half of 700 is. And then you would have just had that 500 and that 350, and you could also add that to be that 850. But I've got some people over there that are talking about half of, didn't I see it? I thought I saw it. Maybe I didn't see it. Anybody thinking about half of 1600? Do you know, often I'll get kids that will say that. Well, miss, I don't know half of 1700, but I do know half of 1600. That's just 800. And I'll say, well, what's left over? Well, that's 100 left over. Okay, that's just 50. Bam, there's your 850 again. So I believe you when you tell me that your kids can't have, but I bet they can do some things. I bet they can find half of some things. And if they can't yet, then we can have with them and help them sort of get better at those relationships. Hey, it's almost like you guys were sort of thinking like my kid was earlier. Like you don't have to know your fives if you know your tens. It's almost like you guys are saying right now, you don't have to know your 50s if you know your hundreds. That seems like a really important relationship. How come nobody ever helped me learn that relationship when I was learning multiplication? Well, the good news is now you know it and you can help your students think about it as well. We're not done by any means. Next question. Let me just kind of grab this stuff. I'm just going to sort of shift it out of the way a little bit, and I'm going to clean this up a little bit over here. Okay, so we've got one pack has 17 sticks, 100 has 1700, 50 has 850. What if that's way too much gum? Come on. We're only going to have 49 packs. I wonder if there's something up there that you could use to find the number of sticks in 49 packs. I wonder if there's something that you know you could use. Like maybe there's something that we already have you could use. So everybody's thinking, everybody thinking. Y'all, look me in the eye right now. When I put that 49 up there, how many of you said to yourself, okay, what can I use up there? It's almost like you got a little playful and you said to yourself, well, there's 50 up there. Hey, 50 packs to get 49. Like how many of you in that moment got in the brain space of saying to yourself, how can I use what I know? Versus the brain space where you go, let's see, what rule have I learned? And is this the right rule? And then what are the steps? And then you do all that. Y'all, if you right then were in the moment where you were like, ooh, how can I use the 50 to help me get the 49? In that moment, you were mathing. In that moment, you were using what you know, relationships and connections you own to figure out what you don't know yet. Those are the mental actions of a mathematician. All right, a lot of you are telling me that you said, well, 50 packs minus one pack is 49 packs. So then you've got to take the corresponding sticks in 50 packs, subtract the corresponding sticks in one pack. Now, at this point, many of you have been doing the subtraction algorithm for a few years, some of you more than others. Little joke there. And you know that you've been doing that a lot. Your brain right now has a mental pathway that you might have looked at that and said, ooh, I know what to do. That's where you line it up and do the crossy outies and little ones, like you do subtraction. But could we also think about those numbers? Again, I know that you have that mental pathway well traveled. What if we were to create a new mental pathway and then travel it a lot so it becomes your new go-to? What if you said to yourself, well, how can I think about 850 minus 17? Could I think about kind of, I don't know, just like if I'm trying to subtract, it's not about the number line, it's about the relationships I'm about to use. 17, what is 17 made up of? I'm kind of looking to see if anybody, can't really tell if anybody did the one I'm looking for, at least as I'm looking closely or quickly. Did anybody say, well, I could subtract 10? And if I subtract 10, that's just 840. But I was supposed to subtract 17, so I better subtract 7 more. So if I subtract 7 more, then is that 800 and, help me, 33? Is that right? All right, people are agreeing with me. Cool. So it looks like we might have 833. So I can subtract the 10 and then the 7. All right, that's cool. I'm also seeing a few people say, well, yeah, Pam, you can do that. But instead of subtracting 17, I'm actually going to subtract 20. I'm going to subtract a bit too much. All right. What is 850? Subtract 20. Is that 830? Okay. But now you've subtracted a bit too much. This jump of 20 was bigger than that jump of 10. And so if I've subtracted too much, it's almost like I've given you back a $20 bill, but I only was supposed to give you 17. It should have been a shorter jump. What am I gonna have to do to adjust? Oh, ma'am, I better adjust. We better add that 3 back in. Okay, here's the hard part. What is 830 and 3? See how I'm smiling? Y'all, that's a great place to be when you're reasoning, when the question is the answer. What is 830 and 3? Is that just 833? If you get to a place when you're solving a problem where the question is the answer, you were probably mathing. You were probably using relationships and connections so that by the time you got to the answer, it was just kind of there. That's a good indication. If you do that, you can go, sweet, I was just mathing. On the other hand, if you were mimicking an algorithm, chances are super high that you're going to write a number down and write a number down and write a number down and then read off the answer backwards. Probably surprised about the answer because you were writing the numbers in the opposite direction that we read them. That's a good indication if you read off the answer that you were probably fake math mimicking. Now, there's no harm, there's no shame in that. That's the way we were taught. The good news is we can free out of that. We can free out of that and actually math the way mathy people actually math, the way we just did. So a couple different really nice strategies for thinking about 850 subtract 17. I'm just going to grab these little things and tuck them down over here. We'll come back to that a little bit later. All right, y'all. We found the number of sticks in 100 packs. We found the number of sticks in 50 packs. We found the number of sticks in 49 packs. As you did that, I invite you to consider that you just mathed the way mathy people actually math. And in the process, you just built your brain to think and reason more sophisticatedly than it did when we started. Or perhaps you're already reasoning with these strategies. Then maybe I helped you see a way that you could teach your students to reason the same way that you have been. Because we can. Notice how what I just did was sort of high dose you with some patterns. We gave you a pattern, talked about 5 being half of 10, and now we did 50 half of 100. We're using what we know to solve problems. Y'all, mathy people actually use what they know to logically reason through problems. So first thing we did tonight, what does it look like and sound like and feel like to math the way mathy people actually math? Nicely done. All right, the second thing I'd like to do with you tonight is to teach you to see the shark. Let me head back here. I invite you to consider that I think there are 3 distortions that have impacted the way we teach math. These distortions are about the nature of math. So well, just smile for a second. I'm going to show you an image. Ready, everybody? Anybody remember magic eyes? So these can be called a magic eye, or they've also been called an autostereogram. That's the official name. So some of you might right now be like smiling and you're like trying to see it. And some of you are like, oh, I hate these things. So here's what's important right now. It really isn't important right now that you can actually see the image, the 3D image that can pop out. So in a magic eye or in an autostereogram, the idea is that you relax your vision a little bit. Really what you do is you put the focal point behind the image. So your eyes kind of relax a little bit and the focal point's behind the image. And if you can just do it just right, then a 3D image pops out. It's kind of cool. Well, maybe if you can get them to work, it's kind of cool. If you've never been able to get it to work right now, you're irritated with me. So hang on. It's really not so important right now that you can actually make the 3D image pop. What's really much more important right now is that you've had the opportunity to try. Has everybody had the experience to try to make an autostereogram work? Well, you have because you're doing it right now. So you're looking at this kind of like these little dots everywhere. And do you see some kind of squiggles that are kind of vertical? And then do you see kind of a wavy thing like this? Well, if you can get your eyes to do the thing, then I'll just tell you right now that what you can see is a 3D shark. There it is. So maybe you can and maybe you can't. Diana, I know some people, in fact, there's actually a physical thing and some people's eyes cannot make it work. So don't worry about it. Y'all, whether you can see the shark or not, what's really important is right now, go with this metaphor with me. Be a student in a math class. Ready? The teacher shows this. Maybe this is when you're learning the subtraction algorithm. Maybe this is when you're learning division algorithm. Maybe this is when you're learning to add fractions or solve quadratic equations. Like pick a place where you're learning to do something. And the teacher puts something up on the board. Hey guys, today we're going to multiply fractions. We're going to solve a proportion. And a student in your class goes, oh, cool, look, there's a shark. Like as you put it up, the kid sees it. For whatever reason, they have a natural talent for just like seeing a few doses of a pattern and bam, they're, oh, look, it's a shark. And the teacher goes, like, you need to show me the squiggle things. And the kid goes, there's a shark. And the teacher's like, yeah, but you see these squiggle things? That's how you do these problems. How you do these problems is that you do these squiggles and that wavy thing. Like, you got to show me your work. And the kid's like, this is dumb. It's a shark. There's a shark there. I don't know why I have to like do this stuff. Kid walks away a little frustrated. Maybe you relate to that being that kid. Maybe you relate to being a different kid with a different distortion. Maybe you relate to a kid who is looking at the teacher shows the shark and the teacher says, okay, to solve these problems, see these squiggles? Okay, you got to memorize these squiggles. And then that wavy thing, that's how you solve these problems. And you said to yourself, okay, this is what math is. Math is about squiggles. So I'm going to memorize when I see this that I got to do these squiggles and I got to circle my answer at the end. And some of us, like me, said, hey, I'm kind of good at this squiggle stuff. I can squiggle with the best of them. And I was pretty fast at squiggling, and I got a lot of credit for that. Again, imagine my dismay when I realized what I was good at was actually squiggling and not mathing at all. I wasn't seeing the shark. But be another kid who believes the teacher and goes, I'm supposed to do these squiggles and that wavy thing? God, math is stupid. What does this have to do with my life? When am I ever going to use this? Fine, I'll try to do your squiggle thing. This is really dumb. Math is dumb. Does it ring a little true? Be a different kid in that class. One more distortion that I think is alive and well. Could you imagine a kid that sees this and goes, there's a shark? Cool, I want to see the shark. Teach me how to see the shark. Not stop with the squiggles. I don't want to do your squiggles. I want to see the shark. Yeah, I know you want me to write down the squiggles, but like, dude, teach me how to see this. God, why are you holding out on me? Why won't you show me the shark? Oh, math is dumb. Now, be a teacher who was those kids. So be the teacher who's like, there's a shark. Isn't it cool? And you become a teacher and you want to share sharkness with all of your students. You're so excited. And you get in front of your class and you go, y'all, here's a shark. And then you're like, holy cow, only 2 kids can see the shark. Oh, this is why my teacher squiggled. Okay, because the rest of you don't have a math gene. So, all right, weird. Okay, that's why. All right, here's the squiggles. Everybody squiggle. Does that sound like anybody's high school math teacher? Maybe a little bit. Nice people. They want to help the rest of us see the shark, but because they were not in an atmosphere in a classroom where they were taught how to see the shark, they just could see it naturally. They don't know how to show the rest of us how to see the shark. Pardon my sore throat. Be the kid who just believed that math was a bunch of squiggles. Be that kid. Become a teacher. That kid becomes a teacher, and that kid, now the teacher, says, hey, y'all, this is a shark. I don't know why we call it a shark, because it's just really these squiggles. But everybody, really, here we go. You got to memorize these squiggles, this wavy thing. And the kid goes, it's just a shark. And you're like, I know, but you got to show me. Show me the squiggles. You got to do the squiggles. And then the teacher says, hey, if math class is all about memorizing these squiggles, man, we're going to make it fun. We're going to sing and rap and rhyme. I'm going to tell you stories so that you can memorize that this particular image is a shark, even though it doesn't look like a shark at all. It's got all these, because that teacher had no experience, never did real math, never saw the shark. And so how in the world could we expect that teacher to do anything different? So what do? We give them these teaching techniques and these rich tasks, and we say, just put those in front of the kids and it'll magically work. And they're like, how is this going to help the kids squiggle better? No kid is going to memorize the squiggles if I just give them this open task. That's not going to work. We need to drill the squiggles. We need to have better ways of helping them memorize the squiggles. Y'all, there's no way that a teacher could do any different if that's the only experience they have is squiggling. May I invite you to consider that we have some distortions that are alive and well that impact the way that we teach. Y'all, if we just math the way mathy people math, I invite you into the world to see the shark. We can actually see the shark and teach kids how as well. Let's keep building on that. So we math First thing, we math the way mathy people actually math. Second, I just taught you to see the shark. Third thing I want to teach you tonight is to develop mathematical reasoning. Oh, I totally forgot to do a real quick thing. Some of you are like dying to see the shark. I can do this little thing to kind of help you. Autostereograms are created by taking the image and shifting the pixels over in such a way that your eye gets tricked into forming an image. And there's at least part of, it's not really what you see when you can make it work because you see a 3D image, but there's part of the 3D image if we can shift those pixels just so that's part of what the shark would look like. But again, that's not important. What was important is that you've had the experience of trying to see the shark. All right, y'all, before we move on to the third thing tonight, I want to invite you to put a word or two in the chat. What are you thinking about right now? Yeah, Demetra, thanks. Love this analogy. Cutesy approaches that don't have anything to do with the real math. But Salon, can you appreciate? If you think that math is all about squiggling, then what other option do you have? If that's what math is, well, you better make it easier for them to rote memorize and mimic those squiggles. What if it's something different? And in fact, it is, and we can actually help all kids do this. Yeah, I know you wish you could see the shark, but don't worry. I'm going to help you see the math shark. We're going to really, really get good at that. All right, y'all. Thanks. I appreciate those. How frustrating it is to not see the shark. Yeah. And let me give many of my middle school and high school colleagues a little bit of a, I'm not sure the right word here, but can you imagine how unsettling it was for me as a high school math teacher to realize that what I was good at was actually fake math and that I wasn't really mathing at all? Give all of us some grace to say, you can only do as good as you can do. But now that you know better, let's all do better. All right, the next thing I'd like to do. Last thing tonight, what does it mean to develop mathematical reasoning and avoid the traps? So I'm going to open this part with asking the question, what is the purpose of math class? So everybody's thinking, why do we even teach math? What is the purpose of math class? If math class is all about getting answers, then does it make sense to you, and I think it makes logical sense, that a teacher says to themselves, okay, if kids are going to get answers to this kind of question, this is the kind of question tomorrow, let's see, what is the easiest, most foolproof, it's always going to work, kids will never mess it up, by the end of the class periods, they've got them all mimicked, they're circling their answer, they take it home, parents recognize it, everybody's satisfied, sweet, that's how I'm going to teach kids to solve these problems. If the purpose of math class is for kids to get answers, squiggling, then of course it makes sense to do that. I invite you to consider that the purpose of math class is not to get answers. And thank you, Phil Darrow, for that analogy that I just sort of repeated. If the purpose of math class is not just to get answers, what is the purpose of math class? I invite you to consider that the purpose of math class is to develop mathematical reasoning, that we actually want to help kids reason mathematically. Now, caution, this is not just some think better, like, oh, like I'm going to make you a better thinker. No. This is literally reasoning mathematically. That means you own content. Like you're really reasoning the way a mathematician reasons. So I know that this is a little bit busy. Let me kind of outline some things for you here. Notice if you look at the very outside oval, we call that functional reasoning. Y'all, this is the land of the high school where we want kids to reason about functions and relations and graphs and tables and transformations. That is built on and based on proportional reasoning, which is the land of the middle school. And that is built on and based on multiplicative reasoning, which is the land of the third, fourth, fifth, sixth, seventh grade teacher. Did you notice I overlap there? Middle school's got both of these. And then additive thinking is multiplicative thinking is built on and based on additive thinking, which is the land of the first, second, third, fourth, fifth grade teacher, maybe even sixth grade teacher, depending on your standards. And that is built on and based on counting strategies. Now you might say, Pam, that's just our standards. First, kids learn to count, then they add and subtract, then they multiply and divide, then they solve proportions, then they do that stuff no one understands. Little joke there. But I'm going to respectfully suggest to you that it's not just about getting answers to addition and subtraction questions and answers to multiplication and division questions and answers to solving proportions. No, it's literally actually learning new strategies It's literally building your brain to think a different way. It's literally reasoning more sophisticatedly with more and more neural connections. You're literally building your brain to be more dense, that it now has multiple connections to draw on. Whoever it was that said earlier, my kids can't have. Yeah, I believe you. Let's help them have. Who knew that finding half was one of the important things that kids need to do? Let's stop spending so much time on memorizing squiggles and actually help kids find half, because that's one of the important things they need to do. So we can take all that time that I'm going to say waste, helping kids learn to squiggle, and instead wrap it up like a package and hand it to you to spend that time helping kids reason mathematically. My co host on the podcast, Kim Montague, says take all that time that you would waste helping kids squiggle, and I'll wrap it up like a package and hand it to you in a way that you can help all kids really do the major mathematical strategies, that they are reasoning using the important mathematical relationships to build the major mathematical strategies. So one of the things that I'll just mention, Carol Poole and Barry Linscott are two adult educators who have taken my online workshops. And one of the questions they asked me was, Pam, does this work for our students? And I said, who are your students? And they said, we teach adult ed. We teach of all the people who are the most downtrodden, the most that are believe that they cannot math. Can they build mathematical reasoning? My answer to that, just like I say in my online workshops, is yes. In fact, this is what they can do. What they don't typically do well is rote memorize and mimic for lots of reasons. What they can do is use what they know to reason logically to find the answer to questions. So let's dig in just a little bit more. If reasoning is based on each other, if in order to reason additively, I got to be able to count first, that makes sense. In order to reason multiplicatively, I got to think additively first, that makes sense. In order to reason proportionally, I got to think and reason multiplicatively. All of these are based on each other. So we need to help kids continually be building in sophistication. Well, what did we just do? So in the task that we did a minute ago, a few minutes ago, we looked at this pack of gum and we reasoned multiplicatively. We were thinking about 50 times 17, and then we thought about 49 times 17. We were really reasoning multiplicatively. In fact, when you leave this webinar and somebody's like, did you actually learn anything on that webinar? You could say, did you know? You don't have to know your fives. If you know your tens, you can find 5 times anything. Multiply it times 10, cut it in half. And then they're like, oh, that's interesting. You could say, did you know? You don't have to know your 50s. You can just multiply by 100, cut it in half. That's fine. 50 times anything. That kind of reasoning, that's a major relationship. It's one of the major relationships we need kids to own so that that strategy becomes a natural outcome for them. That's a multiplicative reasoning strategy. But in a very nice way, we were also not just developing multiplicative reasoning, but we were developing proportional reasoning. What? Because we started with a ratio of 1 to 17. And then we went to an equivalent ratio of 100 to 1700 and an equivalent ratio of 50 to 850. What's an equivalent ratio, Pam? Well, that means that in every one of these ratios, in those 49 packs, each one of them had 17 sticks. That's an equivalent ratio. Now, we're not done building proportional reasoning by any means, but we've built baby proportional reasoning as we were building multiplicative reasoning. But notice, as we were doing that multiplicative reasoning, I'm going to go down here, look on the left. I was shoring up your additive reasoning with subtraction. This was the problem 850 minus 17. And I sort of helped along by giving you some patterns of how you could actually reason about that problem of 850 minus 17. And how did we reason? Y'all, we were reasoning additively. And you might say, well, Pam, I didn't. I just did the algorithm. And I'll say, yeah, but were you paying attention to what we were doing here? Like I'm gonna take a moment while we're building multiplicative reasoning right here to shore up your additive reasoning. Hey, and also to shore up your dividing by 2, your halving. There were 2 different things that we sort of shored up in the middle of building multiplicative reasoning and, yea, verily, proportional reasoning at the same time. So let's head back here. We want to help students build these successive, more sophisticated kinds of reasonings. Pam, your book is titled Developing Mathematical Reasoning, Avoiding the Traps of Algorithms. What are the traps? Well, let's talk about a very important, insidious trap of the algorithms. We just solved the problem 49 times 17. Would everybody agree? When we were doing that, we solved 49 times 17. That 49 times 17, we should be building multiplicative reasoning. Everybody agree? Like if that's the problem, then kids should be building and using multiplicative reasoning. That's kind of the job of this problem, is to help build those brains. Remember, because the purpose of math class is not just to get answers. Well, if that's true, let's kind of walk through the algorithm. So what do I do first? I do the smallest numbers first, which actually has the high potential to work against kids' intuition. Kids' intuition, when they're thinking about 49 17s, is to say, well, that's almost 50 17s. Like they're thinking about 49 17s. They're not thinking about 9 times 7. 7 times 9, they're thinking about 49s, almost 50. Or maybe they're thinking about 17 49s. It's almost 20 49s. It's more than 15 49s. They're thinking about the relationships. When we first teach them algorithms, we actually work against that intuition. We turn it more into a digit problem, where we say, no, 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 just break everything up into these pieces and parts. It's almost like we're treating them like, you can't think about these big numbers. Just do it with the little tiny numbers. And then we start with the tiniest, most inconsequential numbers in the problem, 7 times 9. So a kid could say to themselves, all right, I'll do this first thing I'm supposed to do. I need 7 nines. 9 plus 9 is 18, plus 9 is 27. And they start adding a bunch of nines. Could a kid do that? Now, I know you wish the kid sort of knew the fact, but bear with me. Could a kid find that 7 times 9 by adding 7 nines? They could, right? They could get this answer correct. Maybe they sing the song of the multiples or something. They put that up there. Now they do this other column. They do this guy over here. Could they then find 7 fours, skip counting, and they could get this correct, and then the magic 0, or the turtle lays an egg, and then they do the rest of them, and then they do all of the addition here in columns and digit-oriented focus, and then they get the correct answer, and their teacher says, yay, you're a multiplicative reasoner. They got the answer right. Are they using multiplicative reasoning? They were actually using additive reasoning the whole time. And that is a trap of the algorithms, that I can look like I've developed a certain kind of reasoning when in reality I was using reasoning in the level before. And we get trapped. We get trapped in less sophisticated reasoning. We get grades. Everybody's satisfied. I took the homework home. I did I repeated all the squiggles. I circled my answer. I handed it back in, and I go on to the next class, and I have no idea what's happening because I was trapped in less sophisticated reasoning, looking like I had attained the kind of reasoning that I should have been developing. That's a huge trap, y'all, that you can look like you're reasoning in a certain way, but you're getting away with less sophisticated reasoning. What was the subtraction problem that we did? Was it, help me, was it 850 subtract 17? Yeah? Is that right? So let's think about that for a second. What if I was trapped in the algorithm? Oh, blast. Can you hold that thought for a second? Head back to the multiplication problem for just a minute. Stay over here for a second. That 49 times 17. Some of you might be saying right now, Pam, my students are not skip counting to find all those. Well, if they're singing the song, that's not even reasoning at all. That's not even on this chart. That's just rote memorizing, mimicking. It's not even reasoning. But you might say, no, 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 they're using multiplicative relationships. When they're thinking about 7 times 9, they're thinking about, well, I need 7 nines or 9 sevens. Ooh, I could use 10 sevens to find 9 sevens. So I just get rid of 1 7. No, they're reasoning multiplicatively, Pam. It's cool. My kids are, but notice, if they're reasoning multiplicatively, how big of numbers, if they're stuck in this traditional algorithm, how big of numbers will they ever reason about multiplicatively? Single digit numbers. They'll never think like you did about 50 17s or 49 17s. They don't get the opportunity to actually reason about the real size of numbers. How many times have we said to students, oh my gosh, your answer isn't even reasonable? I invite you to consider it's because we took them out of reasoning land and we put them into squiggle land, rote memorizing and mimicking land. Let's head back here for a second. So here we are. Oh, I hate it when my writing goes away. Sorry. So all that writing that was on there, now it's at least a little cleaner. But do that 850 subtract 17 with the algorithm for a second. If I look over here and I'm supposed to do what? I'm going to borrow and or maybe regroup, however you're going to call it, and I end up with 10 minus 7. Be a student in the algorithm. Could a student at that point go, all right, I've done everything correct so far. I get 10 minus 7. 10. And they literally count back by ones to subtract 7, and they put that correctly down here, and now they go over here and then they think 4 and they count back again. And y'all, could they get this answer correct but the entire time counting by ones? In other words, they're doing the right method, but they're getting away with using less sophisticated reasoning. All right, teachers of higher math, you're not getting away with it or away from it. Or let's make sure we talk to you just a little bit. What if I was solving a proportion? What if I had something like a divided by b equals c divided by x, and I'm looking for x? So I could do that cross multiply and divide thing just briefly. Just briefly. Say out loud with me. Cross multiply and divide. What kind of reasoning is that, y'all? If I do this algorithm to solve a proportion, am I building and developing and using proportional reasoning, or could I get away with using, at best, multiplicative reasoning? And what if they do that cross multiply and divide using the traditional algorithms, which could let them get away with additive thinking? We're supposed to be building proportional reasoning, and they could be getting away with additive thinking because they're trapped in an algorithm. Y'all, this is real. We can avoid the traps of algorithms by avoiding rote memorizing and mimicking squiggles. Rote memorizing and mimicking algorithms that allow kids to use less sophisticated reasoning than the problem is calling for. So the first trap that I introduce you to tonight is the less sophisticated reasoning trap, that I look like I am developing a certain kind of reasoning, but I'm getting away with reasoning in the level before. High school teachers, if you're teaching kids to find the slope of a line, and they literally are counting squares on a grid or counting by ones to find the difference between that x value and that y value, bam, they're back over here at additive thinking. Well, if they're counting by ones, they're counting strategies. Like, what kinds of algorithms are you using that could allow kids to get away with less sophisticated reasoning than the problems are intended to develop? Trap number 2, the digit-oriented trap. What that means is that they take every problem and they turn it not from thinking about 49 17s, but to thinking about all those individual little multiplications, which I can do with skip counting. I take the problem apart into all its little pieces, and then we wonder why kids aren't making sense of anything, because they just had to do a bunch of steps on a bunch of little pieces. We can stay out of the digit-oriented trap by not sending our students to answer getting solutions that just get answers by turning everything into digits. Lastly, there is a definition of math identity trap. What does that mean? Would you consider that if I look at math as memorizing and mimicking squiggles, that it's all about you tell me what to do, and then I just mimic that stuff and I write it all down and I circle my and I'm really mimicking what you showed me to do? If that's the definition of math, then either you're like I was as a student, where you do that well, and then you say to yourself, I'm good at math, when in reality, you're good at fake math. You're mathing it all. It was really, I don't know if you can appreciate how traumatic that was for me when I realized it as a math teacher. I'm so glad, though, that I realized it maybe a little later than I wanted to, but that now I can math. I can math with the best of them. I can actually I'm doing the mental actions that mathematicians actually do. Be that kid who believed that math was about squiggling, rote memorizing, and mimicking steps and procedures, who wasn't good at it. And now we have our national epidemic of people who say, I'm just not a math person. Math, what does that have to do with me? I'm not, math is boring and it has nothing to do with my life, and I'm never going to use that stuff. That definition of math, if we get it wrong and we think that it's about rote memorizing and mimicking, just repeating squiggles, bam, it affects our identity around the thinking and reasoning and the doing of mathematics, who we are as mathers, to quote Deborah Parrott Creighton, who talks about readers read, Writers write and mathers math. Y'all, we can all be mathers if we learn to math the way mathers actually math. Bam. Y'all, I've given you 3 traps of algorithms by mathing the way mathy people actually math, teaching you to see the shark, and talking about and developing what does it mean to develop mathematical reasoning and avoid the traps of algorithms. Y'all, math is actually figure outable, and we can teach it that way. I invite you to join me on the Math is Figure Outable podcast. My co-host Kim and I talk all about figure outable math and how to teach it that way. I invite you to join me on, whoa, I think I just didn't share. I don't know why my computer does that every once in a while. Give me just a second. Sorry about that, everybody. No, that's not what I wanted to do. Oh, Pamela, I can share. I can. Should be there almost any second now. There we go. All right. I invite you to join me on Math Strat Chat, where I put out a problem and the whole world puts in their solutions and we chat about each other's strategies. It's a super good place to build your mathing. Y'all, math is figure outable. I'll leave you with this. When I had that kid who said, Mom, you don't have to know your 5s if you know your 10s. I am so glad that that kid got me thinking about algorithms and what mathing actually means. One day, I was ready to tell the world, we do not need algorithms. They are amazing human achievements, but they are terrible teaching tools. That kid of mine came home one day and he goes, hey, Mom, will you teach me long division? I said, dude, I'm about ready to tell the world we don't need algorithms. Why do you want long division? And he said, I always just ignore what my teacher says and I always just reason through the problems. And I still can, but I've always been done first and I'm not first done anymore. It's kind of irritating. My friends are just like doing this thing. And so it's kind of irritating. I'm not first done. Will you teach me long division? And I said, what are you doing? And he showed me a paper with 50 long division of decimal problems. And I said, oh my gosh, you can reason through all of those? I'll admit at that point I had been doing mostly whole number work. And he goes, yeah, division of decimals is figure outable. So in that moment, I didn't really know how to handle it. What am I going to do? So I just said, fine, I'll teach you long division and then I'll go deal with my existential crisis over here. I was about ready to tell the world. And so I said to him, all right, long division of decimals. The only thing I could think of in that moment was that this number needed to be smaller than that number. Then I would get a decimal answer. And so I literally wrote those numbers down. I'm still kind of fussing with what I think about my kid want long division. And I said, okay, honey, what times 8 is 6? What times 8 is 6? And I'm all ready to prompt the decimal point and the 0 and the decimal point up here and all the things. He took a deep breath and he goes, 2/3, no, 3/4. Is that the right? I'll let you do that long division later, but I'll ask you this. What times 8 is 6? Now, what is 1/4 of 8? 1/4 of 8? Everybody just say it out loud. 1/4 of 8? Is that 2? What are 3 1/4? If 1/4 of 8 is 2, what's 3 1/4 of 8? Is that 6? Sure enough, 3/4 of 8 is 6. I looked him straight in the eye and I said, no, I will not teach you long division. Because you have been thinking and reasoning, you have built your brain to be able to reason more and more sophisticatedly. No, I will not. Y'all, that day, I took a risk. I took a risk with that kid. In fact, I took a risk with all 4 of my kids. He was my oldest. None of my 4 ever wrote, memorized, and mimicked algorithms. Sometimes they'd come home and they go, Mom, is division of fractions figure outable? And I would say yes. And then we would do it together because their teacher gave them invert and multiply and they couldn't make sense of it themselves. So we made sense of division of fractions, not some algorithm. Y'all, all of those 4 kids, 3 became computer scientists, English, and I've got a STEM landscape architect. They all math with the best of them. When the 3rd, computer science, graduated from Brigham Young University with a computer science degree about a year and a half ago, he called me in the middle of his last semester and he said, Mom, thanks. And I said, for what? And he said, you will never guess the class I'm taking right now. And I said, tell me. And he said, Mom, I'm taking a computer science class called algorithms. We create algorithms. And I was like, dude, tell me all about it. And he goes, Mom, everybody who was like you that wrote, memorized, and mimicked their way through class, they're failing this class because they don't understand what's going on. Kids like me who always reasoned through stuff so we actually know what's going on, we can create algorithms. Thanks, Mom. Y'all, that risk, those kids, was totally worth it. I invite you to check out Developing Mathematical Reasoning, Avoiding the Trap of Algorithms, so you can avoid the trap of algorithms and help your students develop mathematical reasoning, because math is figure outable. Thank you so much for joining me tonight. Really appreciate it. I will see you in the Twitter sphere. All right, the Mathersphere. Thanks, everybody.
And I want to thank everyone for attending tonight. And a big thank you again to Pam Harris.
Thanks so much, everybody.